Hi guys, can everyone hear me? I hope you can. So my name is Nick Smith. I'm going to talk about artificial intelligence for railways. A little bit about myself and the company we established in 2012 as a drone technology company and started developing technology and services in 2015, 2016. We now are a distributor, designer and builder of LiDAR hardware and software, as well as we've built some really powerful machine learning platform and commercial deployments. So I'm going to talk not about our product too much, but about the opportunities around artificial intelligence. So what is it? Effectively, it's a group of technologies that allow for machines to sense and comprehend the world around us. This is something that I think is a big opportunity. So why does this matter? It allows for people and technology to supercharge the creativity and skills of people. And where's it going from here? Well, I think this is where it really allows human ingenuity to be enhanced by the speed and power of computational resources. So effectively helping machines to help humans. Some basic foundational introduction into machine learning. So you can think of machine learning as, or computers as a 10-year-old child. A child, to understand and comprehend the world around them, needs to be trained, and we teach our kids in the same way our machines need to be taught. And we do that with ground truth examples or real world data, so that the machines or the machine learning models can learn about the details. The second part of that is actually then deploying those machine learning models and training those into commercial environments. And the last component is inferring the results. So this is where we throw real world data, unstructured, uninterpreted data from the world, whatever it may be, and we use the computers to infer the results. That process is where assets can be detected in imagery, for example, or where measurements can be analyzed from a degradation perspective. There's three types fundamentally in machine learning. There's kind of four, but these are the three primary ones. And as you can imagine, it's a very complicated field. So if you think of this as the top of the tree, there's probably 1,000 other applications and models and details that can be visualized underneath this. The first one is supervised learning. It's the most basic, very much task driven, and it's more closely related to automation than it is to AI. Then there's unsupervised learning. So this is more data driven. So where we can throw a whole heap of samples at a model and then let the machine learning algorithms to define that model. The third is reinforced learning. It's fundamentally where it learns from its errors. So we can think of that as when a mistake is made, it can pick up on itself and understand that it made a mistake and therefore improve the model over time. So as a company, Corridor, I'm just going to go through what we're doing and try and provide you with a bit of an overview in terms of real world projects, and then try to link that back to some of the risks associated with it. So millions of inspections and measurements and tasks are required to ensure a safe and reliable network. Inspections need to be carried out daily, weekly, monthly, quarterly, whatever the interval of asset inspections need to be. So we took a little bit of a different approach to asset maintenance in railways. As we're innovating and trying to be a startup business, we put the thinking cap on as what if every train could be a diagnostic measurement train? And I realized I just spelled train wrong in that slide, so my apologies for that. And so that's what we thought. What would happen if you put sensors like LiDAR imagery and positioning systems on all of the in-service passenger trains, for example, or haul locos? So that's what we did. We started designing the concepts around that, and taking the data from those in-service trains and using machine learning to automate the data processing and reporting process. And you can think of, automating inspections on track and overhead wiring, looking at asset conditions and degradation, as well as looking for anomalies, where it be transit space anomalies and measurements. So this is where I'm going to talk about a project that we've been working on since January. So we were awarded a 3.5 year contract with ARTC, where we would install LiDAR camera and survey positioning systems on board the AK car. The AK car is ARTC's diagnostic measurement train. It travels the entire ARTC network and its clients, about 12 to 13,000 kilometers every 4 months. And so over the last 6-7 months, we've completed 36,000 kilometers of LiDAR data capture and processing since the end of January, using our technology. The primary function of which, and what I'm going to talk to you about and how this relates to machine learning, is the cross-section engine that we developed to do that. So if you look at the image here, if you imagine that all the colored lines were removed, what we have there is a point cloud. Point cloud won't be too unfamiliar to probably most people here, and you can think of that as it is structured data in a way that it's geospatially orientated, i.e. each point represents a point in space. But from an engineering perspective, it's unstructured data. So what our cross-section engine does is it takes the cross-sections of the railway captured from LiDAR system and creates structured data outputs. So we give the engineers and inspectors the data that they can work with. To put some actual numbers and details around it, there are a number of data points that we can extract from using machine learning from those cross sections, and we use what's called a pixel classifier in that cross section to identify the rail track heads. For example, we can also classify the ballast, platforms, gantries, all types of different assets in that cross section. And one of the three, I guess you can think of the foundational spin-off solutions. So we can export the track center lines automatically. We can work out track spacings, again, automatically. We can also model the kinematic profiles of the track and compare those against design standards or the appropriate gauge. We can also do infringement reporting. So using the same cross-section engine, modeling the kinematic or dynamic envelope of the train through the network and looking at outputting the results from an infringement perspective, whether that's vegetation for vegetation management or using it for the reporting of actual infringing structures. So the outputs of this, when it detects an infringement, whether it can classify that infringement being vegetation or man-made, and then report that into a asset management system. Fundamentally, what we're doing with ARTC is using it to update the National Infringement Register. We're just able to do it a lot quicker, purely because we use machine learning to automate it. This video is the actual software running in real time. We actually break the cross sections into 2 meter intervals, and you can see what we can see in this cross section. Fundamentally, this cross section, what I'm showing you in this video, is a image, not a point cloud. So we take the 3D point cloud, put it into a flat 2-dimensional image, because that is where we find the most reliability and accuracy in the machine learning is in our pixel classifier. So in this, you can see what it's doing, working out the structure and vegetation clearances and infringements, looking at the railhead, identifying the track center lines, and looking at track spacing and outputting those results accordingly. So machine learning, the cross-section engine that I've just shown you and gone through very quickly is just, I guess, the tip of the iceberg from a machine learning perspective. As you can appreciate, there's a whole heap of other technologies that goes into that, but the thing that makes it possible is the machine learning algorithms that do the identification and classification. There's a lot of different other applications that the same data, i.e. the point cloud with imagery, can do. For example, automating track patrols, looking at encroachment reporting, asset identification and mapping, and automating the asset change requests process as well. Looking at overhead wirings, low adhesion prediction, as well as a very clear one which we're delivering now, which is ballast profiling. So this is a video, sorry, not a video, this is an image. What this image shows fundamentally is a 4K image frame from a video that was strapped to one of the trains in Sydney trains with them, and the machine learning, all the boxes, what that represents is the machine learning detecting a whole heap of different classes. For example, we can see that it's detecting sleepers and ties. It's detecting graffiti on the right-hand side. It's detecting the signs and the clips as well as switches. So that tied with the GPS location means that all of those detections are mapped to a location in the network. So why does this work now? So fundamentally, we use in-service trains. So we can use in-service trains to capture the data efficiently and cheaply. Using sensors on in-service trains, we can nearly have zero human operator input into the actual capture and processing of that data. Then we can use machine learning or AI to automate the data processing and the extraction of useful data points. So looking at the assets, the classes, the defects, the location of those assets and defects, and then report that data back into the existing asset management systems, for example, or deliver the reports in CSV even to the engineers who are going to be carrying out whatever task it is. So there are a number of risks associated with machine learning projects. One of them is that, and that's not on this slide, is the fact that machine learning is a relatively new area of technology. And from that, I think organizations large and small, even the largest technology businesses in the world, are still trying to come to grips and understand what the power of machine learning can provide. So it is new, and when you have new problems in technologies, change management is a big risk, and moving towards that. So looking at generic problems with machine learning or risks is reinforced bias. So looking at the discrimination or unintended consequences that can come from machine learning. Another one is governance and management of AI models. So how do we manage the power and flexibility and capability of machine learning models without stifling innovation? Another one, this is a big one, is computational and data costs. Machine learning uses high levels of computational power and is expensive to run. It's also very data hungry in that it stores huge amounts of data and uses very large computer systems to run well. And the last one is explainable AI. And I'm a good example of this. I understand what the opportunities are for machine learning, but if you ask me how it works, I'm going to tell you it's a black box. And even our lead AI architect doesn't understand fully the way that machine learning models work. And that means that if we don't have the ability to explain how something works and the reasoning behind that, how do we justify that, especially in a safety critical environment? Because we might not be able to quantify the risks, all of the risks that might be associated with it. So that's my short 10-minute presentation. Sorry for the technical hiccup in the early stages. I really look forward to question and answers and following up with some more questions. So thank you very much.
something that but I'm going to be able to use and it's going to be looking us through natural language processing and how they're using it to make requirements and to define requirements and to make rail delivery more efficient.
All right, thank you, Lorena. I hope everyone can hear me. All right, so today I'd like to share with you some of the work we've been doing on applying artificial intelligence, in this case natural language processing, to our projects in the rail industry. At Shoal, we provide systems engineering and project advisory services to a variety of rail and infrastructure and asset management clients. This work ranges from system definition and requirements development / management, all the way through the life cycle to asset management and the maintenance of these systems. Our work with NLP has been focused on the system definition and requirements development part of our business. So today I'd like to take you through a brief description on what NLP is, before moving into how it can be used in the definition of rail systems. And then I'll take you through a quick case study on some of the work we've been doing and what we are planning on doing to grow our capability. So first of all, what is NLP? At Shoal, we are always looking for ways to augment traditional methods and processes with new, smart tools and techniques. When we discover a form of AI being used to improve the requirements development process, we jumped at the opportunity to add it to our toolset. So natural language processing, or NLP, is a form of AI that gives computers the ability to read, understand, and derive meaning from human or natural languages. All of us probably unknowingly have interacted with NLP in our daily lives. This ranges from basic implementation such as predictive text, which identifies patterns in the language we use to predict what we are trying to type, through to more advanced evolving applications such as Google Home or Siri. If we look at what goes on inside these black box applications, we can see how these techniques can be extremely useful to requirements and system definition, and particularly in the rail industry. So how does it work? NLP uses algorithms to identify patterns within text or speech. So it takes the text, like we can see in the CAD example on the screen, and uses tokenization by breaking up the text into segments or tokens. It then identifies the properties or types of each of these tokens. So in the CAD example, the algorithm has broken up the sentence, identified the properties of each token, and can now tell what the subject noun is of the sentence, what the subject is doing, and what its objective is. For predictive text applications, if we type the cat sat, the algorithm would recognize that we just typed the verb, and so it would predict the next word to be a proposition and suggest something along the lines of on. If we look at the Google Home example on the screen, when asked, "Okay, Google, pay attention," the NLP algorithm breaks the speech up into 3 tokens. "Okay, Google," the command to perform an action; "play," which is the command to execute a search on one of its media applications and begin playing the audio; and then attention, which is the subject of the search. So how can all this help us in the rail industry? One of the key components to designing any new system, especially in rail, is understanding what it is we need the system to do. We then transform these into what is required of the system to satisfy these needs. This process can be seen on the screen here from an Incosi handbook, which I'll talk about a bit more later. Now, if we don't get these requirement sets right, whether they be the overarching business requirements of the system or the requirements of a particular component, we can see major issues later in the project lifecycle and may end up building a system that doesn't do what we need it to do, which can lead to costly rework or redesign. Thus, when we are developing these requirement sets, we need to ensure they are correct and of the highest quality. This is where NLP comes in. Incosi, which is the International Council of System Engineers, have developed a guide as to what characteristics make up a high-quality set of requirements and what rules we should follow during their development. Traditionally, we would check our requirements against these rules. But what if we could run this check via AI? This is where NLP can be of use. We can use the algorithms to break the text of the requirements down into tokens, then run scripts to check the requirements against the rule set. But why stop at just checking the quality of individual requirements? What if we could check if we have included all the requirements we needed to? Different requirement types follow different patterns. So, for example, something shall do something when some condition is met is a functional requirement, or something shall comply with X standard is a design constraint. We can then use NLP to check that our set of requirements contain all these different types of requirements that we would expect of a complete set. For example, have we included a requirement that specifies the gauge of the track for our rail system, or have we missed it out completely and thus our requirement set is incomplete? If we augment the NLP software with extra system information, such as product breakdown structures or component hierarchies, we can increase the breadth of tests we can do and get a more precise measure of quality of our requirement set. At Shoal, we were enticed by the potential of this technology to help us improve the efficiency and quality of how we define and develop requirement sets for rail systems. So this all sounded great in principle, so we thought we'd give it a go and run a bit of a case study. So before we can get into the nitty-gritty of the case study, we had to find a software tool that we could use to implement these techniques. There are a few different tools available on the market. These include IBM's Watson, QRA, and the Reuse company's tools. Each tool has its own pros and cons, but we decided to use Reuse's system engineering suite for the study. The key factor for this was the flexibility and customizability of the software. This particular software was also developed by two of the contributors to the Cozy Writing Guide I talked about a bit earlier, so we had extra confidence in its ability to implement the guide's rule sets. The tool implements NLP techniques using two applications. It has a knowledge manager, which is the database that stores both the rules and the system information. So this includes vocabulary dictionaries, textual pattern definitions, and any specific system information such as product breakdown structures or hierarchies. It also includes the definitions for the rules themselves. We then have the second application, which is the Requirements Quality Analyzer, or RQA, which is the NLP implementation that takes the requirement sets, runs the actual NLP scripting, and then compares the results with the information in Knowledge Manager. So let's have a look at the case study. To test the effectiveness of using the NLP techniques on rail projects, we needed to run a real-life set of requirements through the tool. We decided to use the principal requirement set that we developed for KiwiRail for their Inter-Islander Resilience Connection project. This project involves the acquisition of 2 new rail-enabled ferries and the associated supporting infrastructure, including 2 new terminals with rail connections. On this project, we provided KiwiRail with system definition support, including the development of all their requirement specifications. So for this case study, we decided to use the principal's requirement specification for the terminal located at Picton, which is in the South Island of New Zealand. This particular requirement set had 385 requirements for the Picton terminal that will allow KiwiRail to achieve the desired functionality while still meeting all the different constraints on the system. The set was developed by a team of engineers of varying experience and had not yet undergone any traditional assurance checks. We picked this set for the case study as it included a variety of requirement types, including performance, functional, and safety constraints. So in order to quantify the effectiveness of the techniques, we needed a baseline for the results. We utilized one of our senior system engineers to perform traditional assurance on the set of requirements. He followed our internal processes in parallel to the requirements being run through the NLP tool. For simplicity, we needed to focus this study just on the correctness of the requirements. So the tool was set up to run the rules from the NCOSY requirements guide over the requirement set. To minimize any false errors being detected, all the project-specific terms and acronyms were added to the vocabulary dictionary of the tool. So here on the screen now, we can see the results. The NLP tool picked up the majority of errors that the traditional assurance techniques found. It also detected quite a few that the traditional methods missed. So although the traditional method did actually pick up a few that the tool missed as well, and I'll get into those details shortly. The tool was extremely effective at finding the requirements that violated any of the NCOSY rules that related to the individual requirement itself. For example, the tool found instances of non-singular requirements that traditional checks missed. So the building example at the top, the building shall have a baby changing facility and disabled toilets. This should be split into two requirements, one specifying toilets and one specifying the changing facilities. Traditional methods prove to be more effective at identifying inconsistencies around the whole requirement set. So, for example, some of the requirements referred to the car park, while others referred to a parking area. These are both the same component, so the terminology should be the same to avoid ambiguity. The other type of area that traditional methods missed were around patterns. For example, the station requirement here should have found it should always have a bound on the number of passengers. The traditional method picked that up, but the tool did not. So what did we take away from the case study? The first thing is that the technique can dramatically improve the quality of our assurance processes. The traditional assurance methods used in our case study took around 13 hours to complete, while running the requirements through the NLP tool took about 2 hours, which included the time taken to actually update the dictionary with the project-specific acronyms. The tool found about 67% of the errors the traditional processes picked up. So if we assume that this correlates to a 67% reduction in assurance time, we can see the tool is quite effective. In this example, that would have correlated to nearly 7 hours of time saved. Furthermore, the tool discovered an additional 44 errors that traditional processes missed. Thus, if we augment our traditional approach with NLP and artificial intelligence, we can improve both the efficiency of our assurance processes as well as the overall quality of our requirement sets. The second takeaway from the study is its potential for further development. The study only investigated how well the technique can identify if a requirement complies with elements of the INCOSE guide related to individual requirements. If we include additional system information into the tool, like component structures and specific terminology, we can add additional textual patterns and can significantly improve the effectiveness of the tool and the quality of the requirement sets. So where are we going from here? While we are very excited about the results of the first phase of our study, we want to understand NLP's full potential and how to best implement it into our processes. The next step is to understand how to develop a Rails system-specific NLP tool and quantify how effective this tool can be. We'll look at doing this by building information about Rails systems into the tool itself and adding specific textual patterns and component structures, and then analyzing how much this improves the effectiveness of assurance processes and the quality of our requirement sets. That's all. Thank you everyone for listening.
Great, thanks, Jake. I think we'll bring Nick on so that we can go to the Q&A section. So we've been lucky enough to get a number of questions from the crowd who stuck with us, so that's really awesome. We're all on, we're all visible, all in good light, so that's really great. I might start with perhaps one of the hardest questions, which is for you both. I might start with you, Jake, and then go to Nick. And the question is this technology, I guess, specifically the aspect of AI that you deal with, and I guess in a broader sense, is AI considered commercial now, or is it still experimental? Shall we go with you, Jake?
There we go. Sorry, I was having trouble with the mute button. Yes, I think it's definitely entering into the commercial space. As Nick's pointed out, his company is certainly selling some interesting AI techniques around maintenance, and I think a lot of different places are incorporating it into their processes to improve efficiencies. So I think it's definitely stepped out of that experimental kind of phase and is entering the commercial market. Now, that's not saying there's still a lot of experimental development to go. Even in some of the techniques we talked about today, there's still a lot of details that need to be fleshed out. But I definitely think it's starting to get into the commercial space.
What are your thoughts, Nick, on that one? Is it commercial now, like all of the sort of work you do, or is it a little bit more experimental?
I mean, it's definitely commercial. You look at Google and Apple and all of the big companies, Amazon, they've all got fairly large-scale commercial machine learning offerings. What I think, though, we are very much in a commercial phase, but I think we're not even scratching the surface of what machine learning and artificial intelligence can actually do. If we put it into a rail context and look at what we're doing specifically, yes, we are commercializing, and we have a fully commercialized machine learning models that are doing activities. As I said in my presentation, 36,000 kilometers of rail has been scanned, and we've put our machine learning cross-section engine through that. So that's commercial. We get paid for it. But it is just the beginning. It's raw structured engineering data to the outputs. The interesting thing, I think, from a railway perspective, becomes where you can apply long-term prediction models and those sorts of things from a machine learning perspective to the data that's coming out from those inspections. So using the data from the inspections to then have machine learning to predict the future position of a railway, I think is one of the bigger opportunities that it is there. But it's definitely a commercial now, but still a lot of research and development is undergoing.
I have a perhaps follow-up question for you, Nick, is have you had any success analyzing the condition of trackside structures in the work that you do using this technology?
Yes. So there's a lot of different answers to that, because different trackside structures will have different types of, we call them leading indicators. So obviously a camera and a laser scanner is never going to be as good as a human at sort of detecting if there could or may be a problem. So fundamentally what we do is use remote sensing, so imagery and LiDAR, to, I guess, create a model of the world or the railway itself, and then we use the pixel classifier to detect features and assets inside that. So an example of what can be done, for example, would be looking at sleepers or tires, and the first step to what we do is detect the presence of a sleeper. A sleeper could be, it is a yes or no answer. Sleeper is there or is not. The second component is the classification of the sleeper. And the classification might be timber or concrete or other or steel or whatever it may be. And then the third layer to the detections can be visible defects. The visible defects might be, for a timber sleeper, for example, the presence of rot and deterioration. Now that can, if you can see it in the imagery, then machine learning models that we've developed can detect them. And that's kind of the limitation to machine learning in general, is if a human being can look at a set of data, whether it's numbers or letters or words or images or frequency patterns, and define problems in there or anomalies that would like to be detected, then machine learning can be trained to do that. And we really haven't found that to be incorrect. It's kind of an assumption that we've been trying to break. And so, in the sleeper example, the last point there is we can look at deterioration or rotting, for example, in the sleeper. Then there's other things like measurements and looking at whether things are in tolerance of a standard or not. As I said, there's 1,000 ways to answer that. But yes, we can, but there are caveats around it.
I think it's always really challenging, because the more you automate, the more it feels like you're taking the human out of the loop. I think this might touch on what Jake was talking about a little bit more, because it's language for requirements. So from your perspective, Jake, how do we keep the human in the loop to ensure that critical decisions are made by people with that nuance?
I think in particular around NLP and I suppose other forms of AI, it's really there to augment or assist us, not take over. So the way I kind of look at NLP is it's a really, really fancy spell check. It goes to your requirements, and it can tell you a lot of things about your work, and it lets you focus on, are you saying the right things, not are you saying them correctly? So it allows you to spend your time more on the important details and on the critical decisions around the more complex things, rather than worrying about, have I formatted this all correctly, or have I included the right structure? You can forget about that to a certain extent and really focus on the critical parts of it. And I suppose that's where AI in general really helps, or intended to assist us, is improve that efficiency around some of the less complex tasks, and let us focus on really what we want to.
I guess as a follow-up, because I was thinking about this in the sense that the more efficient we make things, the more automation, we have a social impact. So in both of your work, have you thought about the framework you think about, or the cost to the social economy? Like, do you think we'll lose jobs? Will they become something else? Like, I mean, because I think those need to go hand in hand. The technology is awesome, but what happens to the social economy? Is there any work being done on that, or things that you're thinking about? Or?
Yeah, I think if I can answer that one just very quickly. What we do is we remove people from track. So we can take a track inspector or someone doing a measurement in the rail corridor. We can capture the data that we could use, what they would normally use, i.e., using their eyes and measuring things, and we can put the same person at a desk fundamentally and be able to complete an inspection from a desk, as opposed to entering the rail corridor and carrying out that physical inspection. It doesn't mean that all physical inspections of assets are removed. It's quite contrary, actually. It's about removing the mundane and the applications that are generally kind of fraught with errors anyway. A track patrol is a good example of someone in a high rail or the front of a cab looking for visual anomalies inside the rail corridor. If they're traveling at line speed, for example, in between tracks, it's unlikely that they're going to detect anything other than the most obvious of defects. Whereas if you use cameras, high resolution cameras and LiDAR, then it's going to capture more detail. The machine learning doesn't get tired. It's not dangerous. It doesn't get scared of the train that it's coming up behind it. So fundamentally, you're sort of replacing it. I think long term there will be a shift in human resourcing across divisions of the economy, whether it be that track inspector is now going to be a desktop track inspector, and that's, I think, kind of phase one. Eventually, maybe that doesn't need to happen, but I think that humans are reluctant to trust technology at the best of times until we really do, like Google and Siri and all those sorts of things that are prevalent in our lives. So I think that long term, there will be a shift in the human economy. I don't think it'll be inside the next 10, 15 years. I think we'll see a slow shift towards more desktop-based work, which is what we're banking our business on. So,
I mean, the obvious one with your work, Nick, is that we're removing people from the rail corridor. So it might make that safer. But I think an interesting perspective is Jake's angle. Like in the work that you do, how do you consider risk and safety when you plan out your work using do you think it'll make work safer, less safe? Does it factor into how you're using the technology?
Definitely, but not. Yeah. So when we factor in safety in the work we do, it's not the physical work of creating the requirements, but it's the safety those requirements create down the track in the project. So if our requirement sets are high quality and complete and cover all the aspects they should cover, the project and the eventual rail system is going to be safe at the end. So by using AI techniques, we can be more certain on the quality of our requirements and we specify the safety and ensure that we're creating safer systems through projects, especially with the increased complexity of things and how much a rail system interacts with everything else around it. I think that's really important, and we can use AI to really help there and improve the overall safety of the system.
Great. I have a question here that's specific to Nick. So, Nick, the question is it possible to identify existing drainage adjacent to track and profile of the location?
So was that existing drainage, did you say?
Existing drainage, yeah.
Yeah, so it depends. So again, it's the first answer to that is yes and no. So if you have a scanner that's on the front of a train or the back of a train, like the AK car, it's mounted at the top of the profile. It's got laser scanners and cameras, positioning. If the line of sight from those sensors is can see the drainage, issue, the structure that you're talking about, then yes, we can identify it very accurately and very quickly. One of the more interesting components around drainage is actually looking for drainage issues. So when you've got a 3D model of an entire railway, all types of things can be simulated in terms of identifying, just for one, pooling of water. Obviously, there's time frames around when that is a problem and when it isn't, but it's also around looking at the rate of flow and all the actual topography of the cess, for example, and whether it's got water there or not. So there's a whole lot of rules and things you can put around drainage defects and issues. If it's just about assets and mapping those assets, yes, very much so. We use that now. The trick is with drainage, for example, a culvert is it runs under the track. So you only have a telltale sign, which might be a concrete header on both sides of the track that's visible. But if you can see those concrete headers, and they look very specific to a culvert, then yes, we can detect those and map those with very high levels of accuracy.
Great. I know that we only have 3 minutes, so what I wanted to do with you both was, if you could, a couple of things, share with us a sort of key takeaway. What do you think that all the people who are joining us on this webinar, what's the one thing they should know or take away from your presentation in terms of how they progress? And also, please share your contact details so they can reach out. We have a number of MAD-specific questions, but I want to give back people some of their time this evening. So perhaps we'll start with you, Jake. So key takeaway, and how do they get in touch?
Yeah, so I think the key takeaway is that we can certainly use AI in a lot of different ways, and maybe ways that you wouldn't naturally think of. So I suppose using natural language processing to kind of assess the quality of mission isn't something that naturally spring to mind when you think of AI, but AI comes in many different forms, shapes and forms, and is definitely a way to improve efficiency across all aspects of projects in particular in the rail industry. And if you want to get in touch, my LinkedIn profile, I think we'll share the information, will we, Lorena?
Yes, we will.
Put that up on RTAA. But if you can contact me on LinkedIn if you've got any questions about natural language processing in particular, or ways it can help in rail system design and definition, then hit me up on LinkedIn.
Nick?
Yeah, so from my perspective, the key takeaway is, and this is one of the questions, is, is this now? Is this technology available now? And I think that we're only starting to scratch the surface of what machine learning can actually do for railways. And railways are relatively slow to the mark, I think, in terms of adopting this new technology. That presents a massive opportunity to increase efficiency and increase the quality of inspections, obviously what we do, and increase the frequency. And when you do those things together, the outcome is you should end up with a safer network that's more efficient and more productive. And the nice thing about that and what we've spoken about today is that it is here now. You can reach out to me by contact details and I can show you. We've got a number of case studies that we're working on with Network Rail in the UK and in Japan that are relevant as well. So we're not, this stuff is right now, but there's also a huge amount of potential in the future, and the opportunities are massive in that context. So, yeah, thank you.
Excellent. Thank you both. We very much appreciate you volunteering your time to present to our members and those who are non-members. We also, well, I am personally super delighted that so many of you could join us this evening and took the time out to learn more and ask questions. So what we'll be doing at the end of this is we will send out all the slides. So Nick and Jake are happy to share the information. We'll also have their contact details. So you can reach out directly to them with your specific questions. And we'll also share some of the questions that you asked with them so they're ready when you email them directly with the hard stuff. So thank you. Thank you for joining our webinar, and we look forward to seeing you next time. Thanks heaps. Bye.
Thank you.